Greetings, citizens of Earth, and welcome to today's keynote. You are joining us live from chilly and cloudy Ithaca, New York, home to Cornell University, where conditions for space observation are suboptimal, to say the least. You may have noticed that there's an ever-increasing interest in exoplanets lately, as science and technology are advancing our potential for discovery in mind-blowing ways every single day. And as humans, we're naturally infinitely curious about the potential for life on other planets. Today's guest, Cornell University professor Dmitry Sevransky, is an expert in the detection and characterization of exoplanets. And for clarity, exoplanets are planets that are beyond our solar system. Dmitry Sevransky received his PhD in mechanical and aerospace engineering from Princeton University, where he was a member of the High Contrast Imaging Laboratory. Prior to that, he worked on multiple Mars missions, including the Mars Exploration Rovers, for which he served as panoramic camera uplink and downlink lead. Recent experience has him working on some fascinating projects, which we will learn more about very shortly. Dmitry Sevransky, thanks for joining us in the studio. So glad to have you in.
Thank you. It's really great to be here.
It's an absolute relief to have people in the studio shooting again as well. Viewers, we have exoplanets, far-off galaxies, and new discoveries in space to explore in today's session. So let's cut right to it. But first, we have a couple notes. This event is being recorded. We are live now, but it's being recorded, and it will be available at this very same URL almost immediately afterwards. So you may share this link freely with anyone you know, colleagues, friends, anyone who you think might be interested in viewing this. You may submit questions to Dmitry in the chat, which is you may open by clicking the upper right, the dialog box in the top right of your video player. Open the chat, add your questions and comments there, and we'll get them here on my iPad in the studio. Now, throughout our discussion, we'll be sharing URLs, and by that I mean a lot of URLs. These are external links and resources that will augment the conversation we're having today, so heads up for those URLs in the chat. However, if you happen to be watching this archived recording in the future, these links are available in the overview section just below the video here. So those will be available probably tomorrow morning. We'll have all of these links ready for you and ready to go. But I want to learn a little bit about our viewers first. Find out who's in the audience. I honestly have very little idea of what to expect. So let's launch our first audience poll. I'm curious where our audience is joining us from. Presumably everyone is terrestrially based, but there you go. So shoot that QR code and let us know where you're joining us from. It'll appear in a word cloud and we'll get a sense of where people are checking in from today for our show. So we'll get a sense of that. I'm standing by for results. And then after this, what we'll do is we'll ask you what industry you work in. Again, I'm so curious about who's going to be joining us in the audience and what industry you work in, where you're from, etc. We're good? Okay. I'd like to see some results if you don't mind. Yeah? Okay. Perfect. There we go. So we have some feedback coming in. Where are we joining us from? We got some mostly Americans, a Canadian in the audience. Looks like Canada's overwhelmingly showing up today. All right, we'll see how this one populates for just a moment here. Chicago, there we go. Earth, Rochester, New York, there we go. I'm a Rochesterian myself, so good to see that. Out in the audience, we got some Southern California, Maryland, Toronto, there we go. Okay, so not as much of a global audience as I'd hoped, although we do have a friend in from Brazil, so that's good.
Excellent.
Good to see you. Well, anyway, thank you everyone for joining us. Good to see that. Now, I am curious about this much more than anything else, which is what industry do you work in, right? So some examples. Let's keep it simple. Engineering, physics, education, science fiction writer, what have you, right? Anybody that is kind of curious about this. Looks like we got somebody. Okay, psychology, engineering, Sao Paulo. There you go. Art. Good. I really was hoping that this would appeal to people in multiple disciplines, and it's really nice to see. We got some healthcare going on there. Corporate sustainability. Beautiful. Great. Pretty good varied audience. Good to see people from so many industries joining us today.
Yeah.
So Dmitry, let's get into the conversation. Thank you, audience, for your input, and I encourage you throughout to please send your comments and questions. So every day I wake up to stunning images on my Twitter feed, photos from NASA's Perseverance Mars rover in my Twitter feed. You worked on earlier Mars exploration rovers, as we mentioned minutes ago. On some of those missions, you were involved in the panoramic camera aspect of things. I have a few questions here. So, I mean, what was that like? How did your education and experience lead you to work on some of those seminal projects?
Yeah, what it was like was incredible.
Yeah.
It was just amazing, and I still can't quite believe I had that opportunity. And pretty much straight out of undergrad. And it was really about being at the right place at the right time, because I was an undergrad at Cornell in engineering, but spending a lot of my time over in space sciences. And I took some classes from Jim Bell, who was in charge of the panoramic cameras on the Mars exploration rovers.
Yeah.
And after I graduated, I asked him for a job. He was good enough to give one to me. And I got to work with this incredible project and these amazing people processing and planning for operations on Mars. And it was also pretty much what led me to the rest of my career, because after a while I realized all the people getting to make the really cool decisions had PhDs. So I figured I should probably get me one of those, and, and then off I went.
So technically speaking, were you involved in the hardware itself, the software, the processing of the imagery? What was?
Yeah. So by the time I joined the team, the rovers were there basically, and so what we were doing, what I specifically was doing, was helping the science teams plan for daily operations. So we would start every day off with a meeting. The science teams would talk about what kind of observations they would need to take. And then all of the different instrument teams would go off and would figure out how to sequence the specific observations, and then all of that would get packaged together and uplinked to the rovers, and the rovers would execute a couple of days at a time, and then we do it all over again. And then on the flip side, we would get information back down from the rovers, have to check it out, make sure that the science data was good, that the telemetry about the health of the rover was good, report back, and then just kind of do that over and over again throughout the run of the mission.
So we have an image I want to show the audience real quickly here. This is a shot of opportunity. What are we looking at here? Yeah,
so this is actually one of my favorite things that happened. So what you're seeing, the thing that's glinting over in the left-hand side, that is a part of the heat shield. So that's part of the protective covering of the rover as it came down. This generation of rover, they used what was known as the airbag descent method. So literally, it would puff up these airbags, and then the whole thing would bounce on the ground after it came in, and so it would roll to a stop. But before that happened, it had to come down through the atmosphere, and so it had this heat shield that was ejected, and we just happened to drive past it. And we had the opportunity to use the science instruments, the PanCams, to image part of the heat shield and give this really invaluable information back to the engineering teams. And then all that gets folded into the next generation. And so that was just this amazing interplay of science and engineering and technology and taking pictures on another planet.
Yeah, it's absolutely miraculous. It never gets old, honestly, looking at some of the images that come back. So let's talk about imaging telescopes. You know, what is the state of the science as it relates to imaging and telescopes? I mean, observatories, telescope tech has been around for something like 500 years at this point. For the half century, we've been doing imaging and observation from space. Where are things going? Where are they right now? Let's baseline the conversation a little bit.
Sure. So believe it or not, despite, as you say, you know, Galileo and Newton using telescopes way back when, things are still advancing. And some of the most exciting things that are happening right now have to do with the field of adaptive optics. And so that's literally elements of our telescopes that can change their shape. And we use these on the ground to counteract the effects of atmosphere. And so light from distant stars, planets, whatever, comes through our atmosphere, and it kind of gets messed up because the atmosphere is this roiling, boiling mass of convective cells, and that's not good for optics. But we can undo that. We can untwinkle the stars. And so over the last couple of decades, there have been more and more instruments now fielded at these major observatories in the world that have the ability to do this. And that allows us to do much, much better science from the ground. And at the same time, we can use these in space to create more and more sensitive instruments and basically push the limits of what's capable. So what's happening is we keep getting better at collecting photons from very, very dim things, which means that we keep getting better and better at seeing very, very dim things like exoplanets, and also looking backwards in time, because the further out you look in the universe, you're looking back in time. And so that's the story. We are going to keep improving our ability to push the limits of what we can see, and that will allow us to see more and more things that in the future potentially maybe look like our own Earth, and also push back to the earliest phases of our whole universe.
So back to the adaptive technology, the mechanics of it.
Sure.
What exactly is going on? You had talked about,
So-
an array of mirrors kind of moving.
So really, these devices, the primary device that's at the heart of all of this is something called a deformable mirror. And that's literally, they're very small devices. And so you can kind of think of them all, they're basically tiny mirrors that can change their shape very, very minutely. Not so much that you could see the change in the shape by eye, but enough that it affects light, right?
Yeah.
Because wavelengths of light are very, very small. So you don't need to push these things very hard in order to get a large effect. So we're talking about microns, micrometers of change. And they're small devices with lots and lots of actuators patched in, and they push and pull the mirror, and they change its shape, and the light reflected off of it changes, what's known as the wavefront changes in response to that. And so if you can measure how the light is being aberrated, and for that you need another device called the wavefront sensor, you put these two things in closed loop together, and you can correct for the atmosphere, if you do it fast enough.
So tell me about the Gemini planet imager. We've got an image that we want to show here, right? So there's something that I want to look at here. This is we're observing an exoplanet that is orbiting a star. Tell us a little bit about this project here. This is the Eridani image.
Yeah. So the Gemini Planet Imager is a project that I joined in my postdoc. I was at Lawrence Livermore National Lab. And so what this is a machine specifically built to image exoplanets from the ground. Exoplanets are very, very dim compared to the stars that they orbit. So if you want to see these things, you have to block out the star.
Yeah.
And so there's a bunch of different technologies coming into play here. And so what you're seeing here in the center where there's that little star symbol, that's where the star would be. And the black circle around it is we're blocking it. And that's done with a device called the coronagraph.
Yeah.
And then the bright spot that you see off to the side is the planet. This is 51 Eridani b. And this is the first new planet discovered by the Gemini Planet Imager, which itself is was at this time sitting down in Chile at the Gemini South Observatory. Yes, and so this animation made by Jason Wong it's kind of incredible because you're actually seeing over the period of many years, you can see the counter in the bottom, the orbital motion of this planet.
Yeah.
So this is a baby Jupiter. This star is about 20 million years old, which makes it like a newborn on stellar timescales.
Sure.
And this planet, based on models, we think maybe about 2 Jupiter masses. And the only reason we can see it from the ground is because it is so hot from its initial formation that it is emitting infrared radiation, and that is what our instrument picks up. But before it can do that, we have to block out the star, we have to correct for the atmospheric turbulence, and then we have to do a lot of post-processing, putting the data together. And then even Jason did even more post-processing to make this really cool animation. And so it's in a 30-something year period. And so we're just seeing, basically, we found it in 2014, so we've monitored about a fifth of its orbital period.
So cool to look at. Real quick, just thinking about that. So some of the interference or some of the residual stuff around the edges, that's the atmospheric stuff that kind of gets in the way. We've cut through, right? You can see the planet, you can see the star.
Correct. And then everything, that stuff is called speckle. So it's the leftovers. It's the starlight that we weren't able to get rid of altogether. It's the atmospheric effects that we weren't able to perfectly correct.
Right.
And then there's other noise sources and things happening. So it's a monstrously complicated problem. We're basically now, for the first time in human history, at the point where we can do this from the ground. But we're limited to these very young, very, very hot, large Jupiter-like things. And so we need to keep pushing. Yeah,
so this was earthbound observation. In previous discussions that you and I have had over the past few weeks, there's been discussion of a great observatory.
Yeah.
Suggested that you suggested that advances in direct imaging and upcoming space missions are driving us to build a great observatory that'll pretty much transform the field of planetary science. What are we talking about? What is the Great Observatory? Where does it live? Is there a global partnership? Who's part of building the Great Observatory that we all imagine?
Sure. So the original Great Observatories program was a NASA program to try to basically cover all wavelengths, almost all wavelengths in infrared, of light from space. And so there was a series of 4 space missions, and Hubble is actually the last one still operational out of those. And that was the original Great Observatories program. Now Hubble is going to be succeeded by James Webb. And we're now looking beyond that and at what the next thing is. And the basic consensus is that if we want to discover planets like our Earth, and so go beyond the limitations of just looking at these very young giant planets, we're going to have to do it from space. And for a bunch of different reasons, imaging is one of the best ways of getting detailed information about these planets, these Earth-like planets. But to do that, you're going to need a very, very big telescope in space. And so what is happening right now is there was recently a report from the Decadal Survey, which is a report by the National Academies that comes out once a decade, unsurprisingly. And what they've recommended, one of the things that they recommended is that NASA prioritize technology and mission maturation program for this a very, very large observatory, something that has an aperture of at least 6 meters in diameter, and that is capable of doing imaging in all wavelengths from ultraviolet to infrared, so beyond what James Webb can cover, more like what Hubble's wavelength range is. And this would allow us to do really transformative science in a whole bunch of different areas, including exoplanet science.
There's an aspect of it, the report recommends critical near-term actions to support foundations of the profession that includes education and some of the some of the stuff that you've been involved in, certainly recently, and tech and tools and everything else that's kind of involved in this. Again, sort of a multidisciplinary, multi-institutional endeavor.
Absolutely.
How does this was something that I was curious about. We talked about a little bit about this before the show. So you've got what amounts to a global endeavor, right? Many people from many institutions participating. Describe what that work environment is like. I was curious about the competitiveness of it. There's a cooperational element, obviously.
Yeah.
Many parts. How many people are involved in this? What are we looking at to pull this off?
Literally thousands, thousands upon thousands of people. Because to do something like this, so huge, so cutting edge, so new, you have to pull the best talent from everywhere.
Yeah.
And so these modern science collaborations, they're group endeavors. There's not, there's occasionally an individual who's a driving force behind an aspect of this, be it the principal investigator of an instrument or of a smaller mission. But when you're talking about these enormous missions, you're talking about hundreds and thousands of scientists and hundreds of thousands of engineers, both working in academia, working at NASA centers, working in private industry for the prime contractors that make the hardware that eventually goes to space. So this kind of science is done in groups, and that means that the people who do it tend to be the people who play nice with each other. And so it's really a lot of fun because you end up working with the smartest, most talented team players in the whole world.
All right, let's back up a little bit. So talking about exoplanets, in the last 30 years, there have been discovery of something like 4,500 exoplanets orbiting stars, outside of our galaxy. One in five sun-like stars have an Earth-sized planet that measures somewhere in the habitable zone. So when we're observing exoplanets, many different ways to do this. What are characteristics? What are attributes that we're looking for? What are we gleaning from our observations?
Honestly, it's whatever we can get. We're trying to squeeze as much information out of all of our observations as possible. But as you said, there's different ways of finding these things. And each method kind of defines what's possible, what kind of information is possible. And so the earliest discoveries came by looking at the stars, and the stars are pulled back and forth by the planets orbiting them, and that causes a Doppler shift in their color. And so we can track that, and then we can get what's known as the radial velocity. So that's just the velocity along the line from you to the star. And so that allows you to measure the minimum mass of the planet, not the true mass, but the minimum mass of the planet can have. And you can measure the orbital period. And you can measure a couple of other things about the orbit, but not the full thing. So we get a line of information from that. And then there's something called the transit method, where you wait for a planet, you basically wait to get lucky, and for the planet to come in between the star and you. And so the star dims momentarily. And that's known as transit photometry. And from that, you get a proxy measurement of the planet's radius, for example, but not anything about its mass until you can fit a fuller orbit, and then maybe. And then you can also start to get some spectroscopic information from that. And then you have imaging, which gives you a snapshot of where the planet is, but projected into the two out of the 3 dimensions that the orbit actually is in. And so you start putting all this information together. And so yeah, this is just a little historical animation.
Oh yeah, what are we looking at here?
So this is something that I put together every year, updated with the newest findings, and there's a bunch of different versions of this that you can find on YouTube. But basically what you're seeing is a map of the sky, and then in time, the discoveries coded by the different methods. And so there's the transit method, the radial velocity method, imaging method. You'll see that by far transits and radial velocities dominate, and especially because there was a mission called the Kepler mission, the Kepler telescope, which actually is single-handedly responsible for over 60% of all of the known exoplanets. It was this transit mission that was just staring at 150,000 stars and waiting for those blips of the planets passing, and it did enormous science that way. And so now we're trying to push forward and actually get light from these planets and add to the information that we have about them and find new ones.
You know, you had mentioned like spectral imaging. Can we learn about things like the temperature of a planet, what its compositional makeup is, the chemistry, its relative age? I don't know how that's, you know.
So for age, we assume that planets are basically the same age as their stars.
Okay.
Getting a star's age is non-trivial. It's very, very hard, but astronomers have a lot of clever ways of figuring out proxy measurements that help kind of pin down the age of stars. So that's when we say that 51 Area B is 20 million years old, what we're really saying is that we think that the star is 20 million years old.
Sure. Right.
And then in terms of composition, yes, when we start sensing, when we actually start getting spectroscopic data, many wavelength measurements of the atmospheres and potentially the surfaces of these, then we can start figuring out what these things are made of. Very much like what the Mars rovers are doing. They're taking multispectral imaging of things on Mars, and from that, from the spectra, we try to figure out what the composition of the rocks that we're looking at. So we can do that for exoplanets if we get that spectroscopic information.
Thank you so much. Turns out live audience questions are pouring in. I've got a question from Mike Alexander. I'd like to take these more than my own questions, to be honest. Regarding the description of adaptive optics, is a laser still used to probe the atmospheric turbulence and feedback to the deformable mirrors?
So in many cases, yes. So there's the concept of a laser guide star, and there's a concept of a natural guide star. So a natural guide star, you're using a naturally occurring source of light in order to make the measurements of what the wavefront, of what is happening to the wavefront, of what the atmosphere is doing. The problem with that is that sometimes there's not a convenient bright star in your field of view to look at. So a while back, people decided to start making artificial guide stars. And you do that by shining a laser at the layer of sodium that's about 90 kilometers up in our atmosphere and basically creating an artificial star. And so that's known as a laser guide star. And so at this point in time, all of the big observatories, the major 8 and 10 meter observatories in the world are equipped with laser guide stars. And there's instruments that can use that information in order to drive their wavefront sensors and feed information to the deformable mirrors. The Gemini planet imager, GPI, is a natural guide star instrument. So we're actually using the light from the star that we block in order to do that atmospheric correction.
Perfect. Thank you for that question. I think it was Matt. Chloe asks, you mentioned that when you view a planet, you are looking back in time. So if you found a planet with life, would you be seeing as it was maybe a million years ago, millions of years ago? If that planet with life viewed Earth, would they see dinosaurs and prehistoric creatures conversely?
Sure.
Thank you, Chloe.
That's a great question. So it's a very linear relationship. The further out you look, the further in time you're going back. The whole idea of looking back in time is just because light travels at a finite speed. And so the light that we see today originated back however many years it took to travel from the source to us. So in the case of 51 Area, that star is about 100 light years away from Earth, so the light that we're collecting today originated 100 years ago. If we were to be able to image a planet that was 1 million light years away, then yes, that light would have originated 1 million years ago. But it gets much, much harder. The further the planet is, the harder it gets for lots and lots of reasons. And so really, we are just focusing on the things that are quite nearby in the local region of space. And so we really are talking about centuries and not millennia or millions of years. In terms of dinosaurs, that's a really fun thing to think about. And I just want to be clear, we're not talking about, at this point in time, resolving features. We're basically, the whole planet is a pixel. And so we kind of get the whole thing in a single pixel. So we're not resolving continents or any kind of features, but there's concepts for the far future of how we might be able to do that.
Yeah.
But the atmosphere of the Earth was different back when the dinosaurs were around. There's more oxygen. That's what allowed creatures to get so big, biologists believe. And so by making bulk measurements of atmosphere, we could say something about an exoplanet if we found one that had a terrestrial-like atmosphere, and we could compare it to what we think historically the Earth looked like.
Great answer. Great question from Chloe. Let's talk about telescope tech.
Yeah.
So, the Hubble is perhaps the most well-known and renowned of telescopes. There's the James Webb Telescope, which is scheduled to launch very soon on December 22nd. It's a joint effort by NASA, the European Space Agency, the Canadian Space Agency, and it's of course planned to succeed the Hubble as NASA's flagship astrophysics mission. Then there's the Nancy Grace Roman Telescope, an infrared space telescope currently in development. That's scheduled to launch in May, 6 years from now, in 2027. Tell us about that project, because you were directly involved in the Nancy Grace Roman Telescope project.
Yeah, so this is incredibly exciting. The Nancy Grace Roman Space Telescope, named in honor of Nancy Grace Roman, who was a major figure in the history of Hubble, actually. So there's this really cool continuity there. She's one of the people that can be said to be most responsible for ushering Hubble through. And so that mission started its life known as the Wide Field Infrared Space Telescope. It's a dark energy mission. It's trying to make measurements the primary mission is to try to make measurements that help explain this thing that is kind of a placeholder. It's called dark energy. We think that it's most of what the universe is, but we don't have a good handle on what it is, and so we need to make more measurements. But along with that primary science instrument, it is actually going to host a technology demonstration called the coronagraphic instrument, and or the coronagraphic imager, and that is an exoplanet tech demo. And so that, for the first time, we're going to be doing this kind of exoplanet science from space that we're doing out on the ground. And so the CGI has a coronagraph, it has deformable mirrors, and so it's going to try to demonstrate the same kind of measurements that we've been doing from the ground from space. And so my group has been working with people at NASA and people at the Jet Propulsion Lab to try to plan out that technology demonstration, and also thinking about what we would be able to do with that instrument going forward if it's successful as a tech demo and then can go on to do science. And so there was an animation just a little while ago. I don't know if we can get that back.
Sure.
So what you're seeing here is very stylized. This is made by software that my group makes, which is a mission simulator. And so what you're seeing here is trying to, basically make a straw man design of what a mission could look like, where you're doing exoplanet science and other kinds of science. And there's a lot of moving parts to this. And so those teardrop shapes are basically where the sun, the moon, and the earth are from the perspective of the telescope in time. So you can't look at those because they're bright.
Sure, okay, I see.
And then the little dots flashing in and out are simulated observations. And then the other dots are potential future observations, and the code in the back is trying to optimize the allocation of time. And so that's one of the things that my group works on in relation to this project.
That's great to look at. Let's back up to the James Webb Telescope, because presumably a lot of what's going to be learned in this particular mission will be, inform what's going to happen with the Nancy Grace Roman.
Yes.
So we have expectations about what we're going to be able to learn with the James Webb Telescope. Is there talk about the potential? What is the potential to learn maybe possibly new game-changing things? I mean, what should we expect to see from those images?
Yeah, so James Webb will be transformative, just like Hubble was completely transformative.
Yeah.
James Webb is an infrared telescope primarily, so one of the things that it's going to be great at is pushing back towards the earliest history of the universe. Not all the way back, but kind of a stepping stone towards looking back as far as you can go. So we'll be looking at the first quarter, about, I think the predictions are 250 million years after the Big Bang.
Do we have anything close to this capability currently?
No. You have to go to space. You have to have a giant aperture. You have to have instruments optimized in the IR. You know, James Webb is the first machine that really will be able to do the kind of science that it's predicted to do. It's also going to do exoplanet science. It's going to try to image it's going to try to do transit photometry of some known exoplanets, maybe find some new ones. There's a currently ongoing mission called TESS, which is a follow-on to Kepler, which is producing hopefully good targets for James Webb to follow up on. And so just like Hubble, James Webb is going to push us in many different directions. And it's going to find things that we don't know about yet. When James Webb was first formulated, exoplanet science wasn't even really, it was a theory. There were
Yeah.
confirm,
Right.
the earliest formulations of James Webb as the next generation space telescope were in the early 90s. The first confirmed exoplanet is 95. Some data before that, but really at the same time that this mission matured, exoplanet science became a thing.
Wow.
So James Webb is going to teach us fundamentally new things that we can't predict yet.
And I kind of interrupted you when you talked about how far back we can look.
Sure.
What was that number?
So I believe the prediction for James Webb is the maybe as far back as 100 million years after the Big Bang. And more conservatively, maybe 250 million years. But we're talking about looking back almost across the entire history of the universe, so that full 13 billion years. The furthest you can look back, theoretically, is to the cosmic microwave background, which is more like 300,000 years. But for that, you need to go even longer wavelengths and possibly even bigger apertures than James Webb.
It's really exciting. So when this launches on December 22nd, you had talked about the deployment taking a little while, it getting where it needs to go. How's that play out?
Yeah, so it's going to be very nerve-wracking, especially for the people directly involved in the mission, but I have every confidence that it's going to go off well. James Webb, unlike Hubble, is not going to be orbiting the Earth. James Webb is going to orbit basically an empty point in space, but a very special empty point in space. It's called a Lagrange Point. It's where the gravity of the Earth and to a lesser extent the moon, is balanced by the gravity of the sun. And you can find, in theory, these basically stable orbits around empty points in space. And in reality, the theory doesn't quite match reality because the theory is you're just considering Earth and the sun, and of course the solar system is filled with other stuff.
Yes.
And then there's other effects other than gravity. But you can help those orbits along with a little bit of thruster activity. And so that point is great because it basically follows just outside of Earth's orbit. And so where, from James Webb's perspective, when it's in its final orbit, when it looks out, it's looking out into dark space, and the sun and the Earth are in the same direction behind it. So it's going to take a little while to get there, and then it has to unfold all of its pieces, and then it has to align all of the elements of its primary mirror. Because it's a segmented mirror, it's not a single sheet of glass, and so those things have to get aligned together. Everything has to be calibrated, worked out, and so it's going to be months before we get the final science grade images, but hopefully we'll know pretty soon after it gets to its final orbit about the state of health of the instruments.
Good. It looks like we're looking at, golly, I'm not sure. Oh, there we go. Yeah, so this was probably the James Webb. No, maybe not.
I'm not sure what this is.
Anyway, we'll cut to something else. The Carl Sagan Institute was something we were talking about before we got started today. Carl Sagan, a famous Cornellian, right? He had a residency here and worked for a number of years here in Ithaca. Carl Sagan, is an American astronomer, planetary scientist, cosmologist, astrophysicist, astrobiologist, author, and science communicator. And again, he's famously spent some time as lecturer at Cornell. You are a member of the Carl Sagan Institute. What goes on there at Cornell, and who are the members?
Yeah, the Carl Sagan Institute is this very cool thing. It's a multidisciplinary organization composed of faculty and researchers from all over Cornell, who all share this common interest in the search for life elsewhere in the universe. And that can be life in other planets or moons of our solar system. It can be life on exoplanets. It's just this general thing, but it's such a deep, complicated question that you can attack it from essentially any direction. And so we have members from engineering, we have members from astronomy, we have members from biology and chemistry and molecular biology, and all people who have kind of a piece of the puzzle. And in terms of what we do, we get together, we discuss ideas, share what our research is, sometimes work on proposals for new research, and also look for opportunities to work with people from outside of Cornell who are doing their bit of the puzzle. So it's really this very, very cool thing.
How would you describe Carl Sagan's particular impact on you? What was your first exposure? How do you measure his legacy? How do we talk about him now? It's been some time since he passed. Yeah,
it's hard because he contributed so much in so many different places. I think that the biggest debt that we owe to him is as a single voice pushing for this vision of exploration, for understanding humanity's place in the whole universe. And that informed the visions of so many people that came after him, many of whom were responsible for the very cool things that I've managed to participate in over the years. And so in terms of planetary exploration, a lot of that vision is due to Carl Sagan in terms of the whole idea of astrobiology and the search for life elsewhere. A debt is owed to the vision of Carl Sagan. So I think in incountable ways that he has impacted my career.
Yeah, immeasurable impact. Audience, real quick, I want to check in with you and see how you're all doing. There must be questions out there, so please submit your questions in the chat. We have quite a bit of time left, so we'll take those, send them my way, and we'll get to them in some way, hopefully in the order that they come in on. So upcoming space missions, there's much more going on, right? We have the James Webb launching presumably sometime in December. What other missions are in the works? What can we expect in the years ahead?
I mean, there's tons of science missions. There's planetary science missions and astrophysical missions. Of course, Nancy Grace Stroman is particularly important to me. But there's also a kind of a constant stream of small technology demonstration missions that are designed to advance our capabilities. And there's a couple of really cool things coming up on the horizon. One of them is and I'm completely blanking on the acronym for a second, so maybe you can help me out.
OSAM-1 or ACS-3?
Yes, OSAM-1 is a technology demonstration for various manufacturing and servicing capabilities in space. And so one of the things that it's going to actually try to demonstrate is 3D printing in space. We've done some limited amounts of 3D printing on the space station, for example. But this is actually going to try to print a structure that could potentially be a useful piece of a spacecraft. And that's huge, because if we can do that, suddenly the scope of what we can accomplish has just exploded. Because when you're building something completely on the ground, you're severely limited by what you can launch. The mass of it, the volume of it, because the various launch vehicles have limited payload varying sizes, and so you're limited right now to something basically 5 meters in diameter. In the future, maybe 10 meters, but that's a strong limitation, and why Webb has to fold up so much. If you can instead assemble chunks in space, or if you can print them, that would be huge. And then the other big piece is that you need to make sure that things that will live their whole lives in microgravity, where they're not really stressed very hard, have to survive launch, which is many gravities of acceleration. And so there's this disconnect between building things to survive launch, but then that don't have to ever experience those kind of stresses again. If instead you can print them in space, you could ignore that whole launch thing, those stresses, and build these very, very fine structures that would never survive launch, but are perfectly fine in the microgravity environment.
I was looking at the notes for the ACS-3, which seems really interesting. Talk about propulsion using sunlight. So what does this look like? What can we
so that's the other
there?
cool. There's actually a number of solar sail demonstrator missions. So solar sails are actually quite an old concept, described in literature and in science fiction for a long time before we ever tried flying them. But the basic idea is that even though photons, the light doesn't have mass, it has momentum. And that means that that momentum can be transferred. And so these things work like sails, like sailing ships, except instead of wind, you're using the captured momentum of photons from the sun. Or you can make a laser sail and fire a laser at these things. And so ACS-3 is going to be one of these upcoming demonstrator missions. The idea is you send up a small spacecraft. It's got a bundled up sail made out of mylar and Kapton, and then the sail releases and covers a very large area, and then captures sunlight and gets pushed along. And so you're talking about very, very, very small accelerations, tiny, millions of what chemical thrusters can produce. But again, in space, outside of a gravity well, that's enough to get you somewhere. And so there's concepts moving forward for, how could we ever think about sending something to other stars? We would never be able to carry enough fuel, but what if you didn't have to carry the fuel? What if you were propelled by sunlight or laser light? And so there are things like the Starshot project and other concepts going forward, but we now actually have missions on the books that will try to demonstrate some of these core technologies.
Have we ever road tested or space tested this kind of tech?
Yes. So there was the Icarus mission, which was a JAXA, a Japanese space agency mission, which flew by, it was a solar sail that flew by Venus successfully. The Planetary Society, which is a private organization interested in such things, has now 2 light sail missions that have basically they're not going anywhere. They're in Earth orbit, so the light isn't enough to overcome the gravity at that point. But they can measure the effect, and they can basically verify that it works. So yes, we actually have tried these things, and I think we're going to keep trying more and more of them.
That's amazing. Let's talk about next-gen astrophysical observatories. We're talking about the Large Ultraviolet Optical Infrared, the Habitable Exoplanet Observatory.
Yes.
What's up with these observatories? Where are they in development and so on?
So these are concepts, mission concepts. We touched briefly on the decadal survey.
Yeah.
As part of that process, the community brings proposals to the table, and some of these proposals take the form of very, very well-developed mission concepts. And so LUVOIR and HabEx, the two missions that you mentioned, these were proposals for observatories that could do general astrophysics and also look for potentially habitable exoplanets. And so over the course of several years, these very large teams made these very, very detailed designs on paper and computer and simulation of these particular observatories. And they actually did many different flavors of them. LUVOIR came in at the end of the day in a 15-meter version and an 8-meter version. This is the diameter of the primary mirror. HabEx came in many different flavors, largest of which was 4 meters. So at the end of the day, the decadal panel did not specifically prioritize either one of these by name. Instead, they said this is very compelling science. And so what the priority is a technology maturation program that will allow you, hopefully in the 2030s, to start construction of a general purpose astrophysics observatory at the 6+ meter scale that is capable of exoplanet and potentially habitable exoplanet imaging.
So the 6+ meter scale you were talking about, I've heard you mention that a couple times. Where are we at now?
So it's a little bit
what
tricky.
does that really mean?
Yes.
Like, I'm trying to envision this.
Yes. So Hubble is a 2.4 meter mirror, but it's a solid mirror, right? So it's a single piece of glass.
Yes.
And that's its primary mirror, and so that's the collecting area.
Yes.
James Webb is 6.5 meters across, but it's not a solid mirror. It's made up of hexagonal segments.
Right.
And they're not completely flush with each other, and so the actual area is less than the effective area of a 6.5 meter circle. And so you get into very nitty-gritty technical detail, but essentially as a single number, we need, the decadal panel said that you'd need the effective collecting area of something that's like a 6 meter mirror across, and it could be segmented because it's very hard to imagine sending up a solid 6 meter mirror, launching that, unless you can manufacture it in space.
Right, precious cargo. Good audience questions coming in. Ken Huber asks, how many exoplanets have been identified that may support life? Are we getting into that business?
So we're creeping towards it.
Okay.
And so right now we can make, when we figure out things about the planet's orbit, we can kind of start to say whether a planet is in what's known as the habitable zone. And the habitable zone, I should back up and say this is all in the context of life as we know it. There may be other forms of life that exist in completely different environments than what we have on Earth. But we don't know about it yet, so it's kind of hard to imagine that. So we tend to focus a little bit on the terrestrial environment. And there's arguments to be made that liquid water is an incredibly important component for life, and of course essential for life as we know it. So that's kind of what we tend to focus on. And so the habitable zone is a definition where basically you put the planet in a separation from its host star where liquid water could exist. So the whole thing doesn't freeze out or doesn't escape. And so you need that. You need the planet to be in the right place. You need it to kind of be the right size, because if you grow it too much, it stops being a rocky planet like the Earth and verges into a gas giant like Saturn or Jupiter. So to go back to the original question, how many do we know that could potentially? The answer is, at this point in time, based on just those bracketing parameters, we're talking about tens to dozens is kind of the answer out of those thousands. But without getting a lot more information about that, we can't say anything more specific. Which is why we need to build these next generation systems. Because once we start being able to measure the atmospheres of these things, then suddenly we can tell you if they have oxygen. And that's huge, because it's really hard to explain the presence of oxygen without terrestrial type life. It turns out to be really hard to sustain the presence of oxygen if you don't have something constantly making oxygen. And on Earth, that's us, right? Or rather plants,
Mm-hmm.
and then we use that. But
Yeah.
that's the biosphere on Earth.
Okay, so hopefully in our lifetime.
I would really hope so.
Okay,
Yes.
good. Hey, Stuart checks in and asks, how early could planets have been formed in the early universe? Since stars fusing simple elements into complex ones takes time. Do you know what Stuart's getting at here?
Yeah, I mean that's a really great question. So the universe is mostly hydrogen and helium, right? Which we think of as kind of as gases, as nothing. And in order to basically, before you can get to any element that's beyond iron on the periodic table, that's heavier than iron, you need a supernova. You need to start to explode. And so because we have all the heavy elements here in our solar system, that's telling us that our solar system is the result of many generations of stars forming and dying and reforming. And so this is now starting to get a little bit away from my area of expertise, because I'm just an engineer pretending to be an astronomer.
Yes.
But as I understand it, as soon as you can make stars, right, and as soon as you have just a little bit of extra material, you can start getting to the planet phase. So planets could have arisen quite early on in the history of the universe. However, they would not look much like what our planets are, because they'd be much more metal poor. And so I don't know if there exists a great answer to that question. It's certainly something that we will, that astronomers and theoreticians will keep working on. We're not going to be able to get the data that we need to answer that question for a long time, because that involves looking very far out in space, very far back into time. And it's going to be several generations of telescopes before we can contemplate that kind of observation.
Perfect. Great question, Stuart. Thank you for that. So getting back to your particular area of expertise, you're a faculty author of an eCornell certificate program in spaceflight mechanics. That's how we met each other and started speaking. So for this particular program, for the student that would be interested in this, how does this relate to your work on imaging and exoplanets? How does it relate to what we're talking about today?
Sure. So I would say it kind of sits at the level below that. If you're a person who is interested in the engineering side of all of this, in the spacecraft themselves, and into putting things up into space and getting them to go where they're going and then to point at where they need to point, that's what this class is really about. It's a class on orbital mechanics, which is the getting them to go where they're going, and what's known as attitude dynamics, which is getting them to point where they need to point. So controlling the full three-dimensional structure that are the spacecraft, and moving them, and also orienting them. So it's a mathematical physics class that is an introduction to these fields, and it's a very, very kind of rigorous treatment of the math that's involved and the physics that's involved. And I don't know if we can put up some.
We do have a couple
animations.
visuals. How about Earth, Venus? Let's check out this one here, and you can tell us what we're looking at. So this is something that's included in the course itself.
Yeah, this is actually an animation of the results of a homework from the course, where you're trying to figure out a trajectory between Earth and Venus. A lot of times in intro courses, this is treated as in a very, very simplified version, and this is, I should say, also simplified, but kind of at the next level of complexity, where we're looking at the three-dimensional structure. The orbits of Earth and Venus are ever so slightly misaligned with one another by a few degrees, so this is not to scale, but that misalignment makes it non-trivial to figure out the right way to send the spacecraft from the Earth to the Moon. And students in the course will learn to do that. And then the other animation is showing a device called a nutation damper. And this is a device that actually is used to passively reject disturbances for spacecraft that are spinning about an axis. And so the damper is that little red wheel on the side of the spacecraft. And by spinning up, it can reject the wobble that you're seeing and return the spacecraft to this passive spin state that a lot of smaller spacecraft actually use for stabilization. And this is, we study the math and dynamics behind this.
Very cool. Thank you for that. So I hope you're keeping up with the URLs that have been thrown your way in the chat. We've got a link to this certificate program as well that we wanted to take a look at. I've got a couple more questions kind of ready to go here. I have one more from a listener, or a viewer rather, real quick. Ken checks back in again and is curious about the mechanical process that actually allows for modification of the mirrors. I think you touched on it a little bit, but
Yeah.
let's try to paint a picture here. And
Sure.
What are we talking about?
There's a couple of different technologies in play.
Yeah.
One of them is piezoelectrics, and so this is materials that change their shape in response to electrical current. And then the other class of devices, and actually what is at the heart of the Gemini Planet Imager, are microelectromechanical systems. So these are basically printed. You can think of them kind of like computer chips. It's a mixture of silicon and wiring on a very small scale, thousands of actuators, and then the whole thing is coated with a mirror surface. And so you literally, you're sending an electrical current, putting voltage over the stack that pulls and pushes pieces of the mirror. And so this is a general class of MEMS devices. MEMS are everywhere. You probably have one in your pocket right now if you have a cell phone. The gyro, the accelerometer in your cell phone is a MEMS device. The inertial measurement units that we use in cell phones and spacecraft.
Sure.
So this is technology that is ubiquitous and has this very cool application for deformable mirrors.
Very good. Thank you, Ken, for checking back in. So this brings us to some of our last segment for the show here, where we're doing something a little more fun and lighthearted. This segment is called What Did You Bring? So this is where we share something that either enriches our life, enhances productivity, or we just think is just plain cool. So for this edition of What'd You Bring, Dimitri, we're going to start off with you. What'd you bring today?
Thank you. So this is a Lego model of the Hubble Space Telescope. I think this falls under the enriching my life category. This is actually part of a larger Lego kit for it's a whole space shuttle build, which is so much fun and so cool. And I love the detail that they put into this because they made little model solar panels and the top hatch that opens and closes to allow light inside. And it's really fun. I use this a lot as a demo or teaching tool, especially if I'm talking to younger students. It's a really high fidelity rendering of this incredibly transformative spacecraft.
So when I was looking into this, you had told me what you were going to bring, and so this deploys from a space shuttle, right? It sits in the bay of a space shuttle, and has been deployed. Forgive my ignorance, but it's only been deployed once, right?
It was put up once by space shuttle, and then it was serviced multiple times.
Oh, it was?
Yes. Okay. So the Hubble, because it's in orbit around the Earth, and the Hubble was in many ways co-designed with the shuttle, and so many of the design decisions that went into the Hubble Space Telescope were due to the design decisions that were made for the shuttle. And so the orbit is such that it can be supported by shuttle operations when the shuttle was in service. So many times people have gone up on the shuttle, grabbed the hold of the Hubble with the shuttle arm. There's like little things here that you can kind of maybe see that model the things that the shuttle arm grabs onto. And then astronauts would go out of the shuttle, would pull out these boxes. These represent instrument boxes, put in new ones, service the hardware, the computers, the various attitude control hardware, so the wheels that allow the Hubble to point very, very precisely, which is what it needs to do. And so, one of the very sad parts about the retirement of the shuttle fleet is that Hubble servicing is no longer possible. Unless somebody designs something new that could fill that capability. So there's always hope, in my heart at least, but unfortunately it's not looking super likely.
So for scale, how large is this in real life?
So the primary mirror, this backplane, would be 2.4 meters across. You're asking me to do basic math in my head, but on the order of a meter is just a little bit over a yard. So we're talking about quite large, much bigger than a person. And so when you see pictures of of astronauts servicing this, they're basically a person would be that much of the payload box. So it's quite enormous when you think about it.
Is the International Space Station involved in any of this business? Imaging, telescoping, this kind of work that you do?
Sure. There's a lot of great science that's done on board of the space station, and there's a lot of really good technology demonstration that's done on board the space station. The space station is not an ideal environment for looking out because It shakes a lot. You wouldn't
sure.
think it, but
Right. Yeah.
as such things go, it's actually quite a low orbit.
Yeah.
Because that's easily accessible from the ground for people.
Yep.
So it's not the best place to be looking out. It's much better to make dedicated satellites that we can put in higher orbits or in different orbits.
Sure. Right.
That are also just designed not to have people walking around in them.
Yeah,
So
yeah.
the space station does play an important role in terms of piloting new technologies that can inform future missions.
Yeah.
But not so much for astrophysical science. Although it does have particle detectors, which are a different flavor of astrophysics.
What's that?
It's just detecting actual particles, not just light, but
Oh.
things coming from space, from
right.
the sun, from other stars. So that's science that happens on the space station.
So given everything that I had learned today, I almost knew that question was obsolete as soon as I asked it, right? Stability aspect, relationship to everything else that's going on, and the minute detail that's involved in imaging. I didn't have any cool space-related hardware or anything at my house, but I did do some research before, and I found this cool YouTube video clip from a show that's called Off-World. This is episode 23, where the topic is what exoplanets look like in film versus reality. And they begin the show by talking about exoplanets' representation in film. The gold standard is 1956's Forbidden Planet, which may be the first depiction of an exoplanet in film. This video is really cool. They ultimately pull in people that are imaging experts, people involved in space exploration and so on. It's a good conversation, and it augments what Dimitri and I have been talking about very nicely here. You have a love affair with 1956's Forbidden Planet. Tell me about that. It's a beautiful movie.
It's a great movie. Yeah,
Yeah.
I haven't rewatched it in a while, but I remember really, really loving it.
Yeah.
And it's gorgeous. It's nice, and I'm not surprised that people consider it gold standard. For whatever reason, in the 50s and 60s, these early movies, I think part of it was that a lot of it was written by well-known sci-fi authors who really cared about the science and the craft, and so they tended to get certain technical details right. They didn't have spaceships making 180-degree turns in space, like some shows I could name. But so modern sci-fi is a lot of fun, but there was this real attention to detail and craft, and yeah, Forbidden Planet I remember it as being completely gorgeous.
Yeah, we were pretty Mars-focused, I think, at that point, too, culturally, right? All aliens seem to come from Mars for quite some time. Audience, I want to thank you for joining us today. It's been an absolute pleasure. Dimitri Savransky, definitely a pleasure to have you in the studio here. I've learned so much throughout this whole process. Everyone, thank you for joining us today. Again, all these resources were shared in the chat. If there was something that you kind of recall from earlier, just take comfort in knowing that these URLs will all be made available in the overview right below the video here in the future. So if you're watching the recording and we mention it, a URL to be shared in the chat, look below here, and that's where they'll reside. So thank you so much, everyone, for joining us. We'll see you at the next keynote. Take care, stay safe, stay strong. See you next time. Thank you.